Okay, so let's make a start. So today I want to talk about point counting. And that sort of very naturally takes place in the setting of O-minimal structures. And that, in turn, is somehow part of the framework of model theory. So I'll start just saying a little bit about the model theory setting and O-minimal structures, and then point counting, and then somehow indicate how this gets applied. So in model theory, one considers first-order languages. So let's call this languages, which I'll call L, and corresponding structures, mathematical structures. So a typical example is the language of rings, which one typically writes like this. There are the two binary operations and the two identity elements. And corresponding to this is a structure which is usually written with some kind of calligraphic letter to distinguish it from the underlying set. The universe of the structure is a set. And in this structure we have interpretations for all the symbols in the language. Now, these symbols which you exhibit are called the non-logical symbols, because there are also the logical symbols and, or, not, for all, exists, equals, and brackets. And so, somehow more generally, you have some language which has an arbitrary sort of indexed set of relations which can be of varying arities, functions of various arities and constants, and corresponding to that you have a structure, an L structure, let's say, which is again a set, and then you have interpretations for all of those things as suitable functions, relations, and constants. So statements and formulas in the language, which I'm going to indicate in a minute how they're defined, can be, maybe I should just do that right away. So once we have a language, we have various syntactic objects. We have the set of L terms, the terms of the language, which are simply constants or functions applied to constants. And you close recursively under that. So you can apply a function to another. If you have n terms and an n-ary function, then you apply the function to the n terms. And then you have the L atomic formulas. And these include relations among terms, including equality. This term equals that term. This relation holds on those terms. So those are the fundamental statements, if you like, in the language that can be true or false in any particular structure. And then you form the L formulas by closing the atomic formulas under the Boolean relations and quantification over any variable. I should have said that in the language we also assume an infinite supply of variables, which, if you want to be very formal about it, you can call them all x indexed by something, but usually you call them, well, by the usual kinds of variables. And among the L formulas, we have the L sentences, which are the formulas in which every variable is bound by a quantifier. There are no free variables. So when you have a setup like this, you have a language and you have this notion, then formulas in the language, and in particular sentences, can be interpreted as some statement in the structure, which may be true or false. And I should say right off that being a structure for the language of rings does not make you a ring. It just makes you a set which has two binary operations and two constants. And that to be a ring means that you satisfy various axioms, and the axioms are some sentences of the language. And this is really the utility of this setting, is that so many mathematical structures can be put into this setting, not to mention set theory itself, but rings and fields and things like that. All right. So that's the basic setting. And I should say that, formally speaking, one always distinguishes the interpretations of the non-logical symbols of the language from their interpretation. So that's formally one should do that, and we take marks off students when they don't. But of course, habitually one throws that out right away, and of course there's no confusion should arise, because if something is an actual function on a structure, then it's different from the thing in the language. And anyhow, the way this goes is that after you prove the completeness theorem, you have to deal much less with the syntactic side. You don't talk much about. So on the syntax side, you have formal logical derivations and so on. Anyhow, I'll say just a tiny bit more about that. Now, if you have a structure for a language, you might want to increase the language let's just say that. You might have a language, and then you want to consider this language with some new relations, functions or constants, and you have the idea of expanding a structure. If you have an L structure A, you can expand it to a structure for the new language simply by interpreting the new symbols. And a convenient notation for this is to say that A prime, when you want to say that A prime is an expansion of A, you simply say that A prime is A ... So that's the convenient kind of shorthand for saying that A prime is some expansion of the structure A. So having said that, I can already preliminarily say what an O-minimal structure is. An O-minimal structure is an expansion of a dense linear order without endpoints. So it is set A with a strict total order which is dense and which has no endpoints and which has some other stuff, possibly nothing. And it has a key property. It's not just that, it has a key property which I will explain. But that's formally what it is as a structure. it's usually an expansion of an ordered field and there, so you might say curly R is R, and then we've got the order and the field structure and then some other stuff. And is often, especially in applications, an expansion of the real field. So here it's usual to denote by R bar or R alg the structure of the real field, as an ordered field. Let me say that. That's the real algebraic structure, the field structure, called all of those things. And then very often you would have some expansion of that. So a very important one in the subject is the real exponential field. Exp, which of course you might just call R bar with exp, using this expansion. Okay, so that's what it is as a structure. There's a key property that we'll come to. And that has to do with the definable sets. Oh, exp is the real exponential.
So it goes from R to
R to R.
R to R, okay.
Oh, yeah. Yeah. So we'll see that this was really the model-theoretic study of that function was really at the base of this whole concept. What nice can you say about this structure? Right. And so to say that, we have to talk about definable sets in a structure. And a definable set is simply a set in some Cartesian power of the underlying universe of the structure that has a definition in the language. Is definable if Z is equal to the set of x1 up to xn in a to the n, such that it's true in the structure that phi of x1 up to xn, where this phi is a formula of the language. And I should say that when you talk about a structure, let's say in structure A, the structure knows its language. The structure has built in what the language you're considering is, and so a definable set in the structure A is simply a set that can be defined by a formula of the language. Now, having said that, this notion comes in two flavors. Strictly, it should mean that only the constants in the structure should enter this formula. Strictly, only constants from L, and functions and relations and so on. So that's called without parameters. That's called definable without parameters. In O minimality, one always talks about definability with parameters. So in O minimality, it's always with parameters, which means that in this formula you're allowed to use arbitrary actual elements of A, which could be arbitrary real numbers or so on. So if you take in R alg, which is this structure here, definable with parameters equals semi-algebraic. A semi-algebraic set over the real numbers is exactly a definable set there. But if you take without parameters, then it's the semi-algebraic sets which are definable over the real algebraic numbers. And that's because every individual real algebraic number is individually definable as uniquely in some satisfying some polynomial and being in some rational interval. So you certainly can define each one of those numbers. And so you can define all those sets. Good. Now, very important for us. Now, right, so I should also say, maybe I should note that, of course, in the real algebraic field, this less than symbol is definable, simply saying that x is less than y, if x is y, if y is x plus some square. So that having this symbol here doesn't add to the definable sets, but it does change the language. And so, for example, if you want to do quantifier elimination, you better have this present, otherwise you'll be stuck with lots of quantifiers. And formally for us also the O-minimal structure is formally an ordered structure, so I always like to put the order there, even if it's somehow backwards definable. I should have said also that when you expand an ordered field, it's a theorem. If you're O-minimal, then this field has to be real closed. That's just a theorem that you prove. And now I should talk about definable families, which will be important. So definable family of sets, or a family of definable sets. So this is a definable set, is a definable set Z, a subset of A. So we're in some structure A. And a definable family of sets is a definable set in some A to the M cross A to the N, which we view as being the set of subsets of A to the N over the fibers in AM. So if you like, you just view it as Z, as the collection, the family of ZYs in A to the N, Y in A to the M. Of course, as I've written that some of those fibers may just be empty, this is strictly just a definable set in that bigger space. But the projection, of course, Y, which is the projection to A to the M of Z, is definable. Because that, whatever set you took for Z, then you would just take the existential quantifiers on A to the N, for which there is something in the fiber, and that would tell you that this set was definable. So there's no real, there's no real issue that this set, the sum of the fibers may be empty. Right. So now let me talk about strong minimality. Strong minimality. All right, so Gödel's completeness theorem So maybe I should just go back a bit here. So when we have the languages and the structures, we can have a set of sentences so a set of sentences in the language is called a theory. And now you can look at two senses in which some formula might follow from a given set of axioms. And one is that you can derive a formula, so that's from the set of axioms, by the derivation rules. There are some formal derivation rules here. And the other way you can do it is to say that this follows from that if in every structure which satisfies this, these hold. This holds too. So that gives you a syntactic sense in which this follows from this, and a semantic sense. And Gödel's completeness theorem is that those two agree. And it can be equivalently stated as that a consistent set, if you have a set of sentences from which you can't derive an inconsistency, then it has indeed a structure. You can make a structure. And since derivations are finite objects, finite by definition, a derivation of a formula from some set is a finite thing. It only uses finitely many of the axioms, and this implies the compactness theorem. A theory T is consistent if and only if any finite subset of it is consistent. That's sometimes called. And in turn, those are consistent if they can be realized by a structure. So T is consistent if and only if it's finitely realizable, meaning that any finite subset of T, those sentences can hold simultaneously in some structure. And a consequence of this is that if a theory T has infinite models, model meaning a structure that satisfies the theory, then it will have models in arbitrarily large cardinality, because you can simply take your theory and pack it with some huge number of new constants and the axioms that they're all different. And then that is realizable in your infinite structure finitely. And so it has a model which will be some very large structure. And that means that excluding theories that have finite models, which is a subject in itself, but we'll be thinking only about infinite structures, the theory can never determine the structure up to isomorphism. And the best you can do is isomorphism in a given cardinality. That's called being categorical. And the nice example is algebraically closed fields. Algebraically closed fields of a given characteristic, let's say 0 just for, are categorical in all uncountable powers. And that's simply a consequence. In an uncountable power, the size of the field will be equal to the size of the transcendent space, and the two fields will be isomorphic if they're algebraically closed with the same transcendent spaces of the same cardinality. So in this area, so categorical theories are somehow best possible in some sense. And a landmark result in model theory was Morley's proof in 1965 of something called the wash conjecture. That if you have a countable theory, meaning that the language and the language is countable, that is categorical in some uncountable power, is categorical in all uncountable powers, that it can't distinguish them. So that was, well, that was a landmark result of Morley when he proved that. And crucially, it involves this notion of strong minimality. So it turns out that the structures that have this property have to be strongly minimal. And what it means, so minimal, so let's say minimality this is for a structure A. Every definable subset of A is finite or cofinite. So this is clearly true in the theory of fields, because you're ultimately, what you can say in the field is that you either satisfy some polynomial and then you're finite, or you don't satisfy and then you're cofinite. So somehow, if you have sets that can be, well, categorical things have to have this strong property, and the strong, so that's minimality, and the strong minimality is that every structure A prime, which is elementarily equivalent to A, which means satisfies exactly the same sentences in the language, is also minimal. And these notions are really different in this case, in that you can have structures where you, well, those are different, but algebraically closed fields, the categorical things are strongly minimal. And these are somehow the nicest things after the categorical things. And so that brings us to, so now I can wipe out my definable sets. So O minimality or O minimal structures, so I can just make the definition that a structure A, which expands the dense linear order without endpoints, is O minimal if every definable subset of A, and keeping in mind that that means with parameters, is a finite union of points and intervals. And let me not spell it out, but we allow unbounded intervals, right? You can go from A to infinity, so to speak, or from minus infinity up to something. So that's the definition. And another way to put it is that every definable with parameters subset of A is definable just with the less than. Because you can pick out all the points and all the intervals and their parameters are there, and then you just say my set is this. And likewise, if you like, minimality means that every definable subset of the universe is simply definable with equality and parameters. You just say my set of the things equal to this, that, or the other, or the set of things that are not equal to in the cofinite case. And just to say that O minimality is automatically strong. So as opposed to this, the case with minimal and strongly minimal, where there is some gap there, you can have structures that are minimal but not strongly minimal. In O minimality, there is no gap. O minimality is the same as strong O minimality, and this follows by the cell decomposition theorem, which I'm going to describe. And the reason is, if you like, that the exact how finite the thing is exactly coded in the theory. So when you go to an elementary extension, all the sets have to look exactly the same. Right. So O minimality means order minimality. The O stands for order minimal. And it's an analog of the minimality notion for ordered structures. So maybe I should say something about the provenance. Of this notion, which goes back to, starts with Tarski. So Tarski proved that the real field, R ouch, is decidable. He gave a decision procedure which involved elimination of quantifiers for this theory. And in the discussion in the publication about this, he asked if Rx was decidable. He actually asked it about the function 2 to the x, but it's interchangeable. So that's maybe a kind of a natural question. After all, you know, if you put this cosine here, it's definitely undecidable because you'll code up the integers and you'll have all of that. But x doesn't look like it's going to give you any integers. So Van den Dries has a very nice paper in 1982, the Logic Colloquium, where he discusses Tarski's question and notes that the decidability is going to involve a lot of complicated arithmetical questions. You know, is e to the e equal to this rational? Or something like that. And he notes that somehow Tarski's work divides into a number of things. One is the quantifier elimination. One is the structure of definable sets as cells, which we'll talk about. One is somehow this decidability. And he notes that quantifier elimination fails here. That was by an example that was very well known for 80-odd years already. That the decidability is going to involve a lot of complicated arithmetic questions, and that really that was somehow separate from the question of the structure of the definable sets. And he writes down essentially this condition, and essentially conjectures that Rx has that property. So, and he calls it being finite type. So this development of minimality, and as an analog of minimality, is due to this term is due to Pila and Steinhorn, and then with Knight they proved the. So this is Knight, Pila, and Steinhorn. They proved this crucial theorem, which I'm going to state. Right, so if you like, from the beginning, the real question was, is Rx, the whole concept was about this structure, Rx, and so Wilkie, when he proved that Rx is what's called model complete, and hence O minimal, so maybe I don't want to talk about model completeness, but something already observed by Van den Dries was Chovansky's work was around at the time. So Chovansky talked about, if you like, exponential algebraic varieties, or the zero sets of what are elementary functions. So it was already known by Chovansky that the varieties that you would define have finitely many connected components. And the problem was that in Rx you have a lot more definable sets than just varieties. You have their complements and the projections and the complements of, you know, you can sort of, well, it's just much more complicated. So what Wilkie actually proved was the model completeness, that every definable set is the projection of a variety. And the key, the key step is when you take a complement and you have to still be a projection. And then with Chovansky, that proved that this was O minimal. And then I just like to, McIntyre and Wilkie then showed that Rx is indeed decidable on something that's implied by, on an implication of Shanwell's conjecture. If you give yourself Shanwell or something a bit weaker that's implied by it, then indeed this is decidable. And maybe now is the time. So in O minimality there is sort of a number of sides to the story, but one is developing what happens in an O minimal structure. So that'll be the cell decomposition. And the other one, of course, is proving that some structure is O minimal. So there are now two on the board. So this one, where is our alg got to? Our alg is O minimal. That, if you like, follows by Tarski's work, the quantifier elimination, that the definable subsets of A itself are just defined by polynomial equations and inequations in one variable. Rx is O minimal. That was a major achievement. And it's very difficult in general to show this. It's somehow a question of analysis, but it revolves around particularly the sort of the essential singularity and these problems of complements and so on. But in the meantime, Van den Dries observed that something called Rn, where have I written this? Rn is O minimal. This is the structure of restricted analytic functions. And what do? You take the real field and you add every function of n variables restricted to the box, but let me just write over convergent. So you take every function, real analytic, on a neighborhood of a box in 0, 1 to the n in Rn. You restrict it to the box, and you add that as a symbol. And this is O minimal by a famous theorem of Gabrielov from 1968. So in analysis, you have the notion of a sub-analytic set. These are essentially the bounded or restricted sub-analytic sets. And Gabrielov had proved that the complement of a sub-analytic set is sub-analytic. And locally, that means that, that implied this. And then maybe I should write the one more. So Van den Dries and Miller proved that you can take Rn and add exp, the full exponential, and that's O minimal. So that's Van den Dries and Miller. And this is the structure that is generally used in applications. Now, at a similar time to this development, Grothendieck had his thoughts about tame topology and the fact that analysis was, or the topology was somehow invented by analysts for their purposes. And so this somehow fits into that scheme of Grothendieck and his tame topology. Because these O minimal structures, as we'll see, they are tame. You can't somehow define pathological things. Dimension theory is nice, stratifications, all of that, which I won't be going too much into. On the other hand, in the applications, it's crucial that you do have these, that you do allow these exponential-like functions which have an essential singularity. Exp is not in here. The full exp is not bounded analytic function, restricted. It's not definable in this structure. And that turns out to be very crucial, and it's then interesting that in fact, the whole notion of O minimality was basically invented to study just that kind of function.
Can one say like what it means to be sufficiently like an exponential function that you can throw it in and still get O minimality? I mean, why this one particular function?
Yeah, okay, yeah, true. So you can take something more general. There's something called the Pfaffian functions. Which are solutions of a triangular system of differential equations. I haven't brought, but I mean, f prime equals f is an example of that, but you can allow functions and then you take polynomials and several variables, and at each stage, if the partial derivatives are polynomials in themselves and everything previous, that's a Pfaffian function. And you can prove, so this theorem of Speisiger, that if you have an O minimal structure, that came later, of course, somehow. So it came later that if R something or other, let's call it RF, is O minimal, then you can form its Pfaffian closure, and that's O minimal. So that includes this, but it came later, of course. And, well, there are various other examples where the quasi-analytic...
And what about things where you have like uniform on the whole real line limits of things that you already had?
I'm not sure exactly...
Or what about limiting processes of some sort where you have control? Well,
many limiting processes you can express in the definability. So, for example, if you get f... So I'm going to say it in a minute, but if a function is in an O minimal structure that expands a field, then it'll be differentiable at all but finitely many points, and the derivative will be definable because you have the usual definition. So you can, and in fact, you can take very general limits. So I forget now, we were talking about this yesterday at lunch. What you can take Hausdorff limits of definable sets. You can take quite general limits. Yeah, so in fact, yeah, so this theory gradually produced all these examples, the quasi-analytic classes, and which also proved that you have incompatible O-minimal structures. There are structures that you can't combine if you go this, right, so they're, but yeah, but whatever you have, you can always take a Pfaffian closure. Right, so let me talk about cell decomposition. Cell decomposition theorem. Yeah, so I need to say first that a definable function is continuous except at finitely many points. A definable function on an O-minimal structure is continuous except finitely many points. I'll say just a little bit more about that, but let me also say that it's customary when you're talking about O-minimality to just start talking about definable things and leaving unsaid that definable means definable in an O-minimal structure. Although sometimes it means definable in an O-minimal structure over a field, and sometimes it means definable in an O-minimal structure over the real field. But for the moment, we can just say that it means definable in an O-minimal structure.
And it means the graph is a definable subset of
yes.
the product?
Yes, that's exactly, yes, thank you. I should certainly have said that. It just means the graph is definable. So now we have a definition of cells. So a zero cell. So now I'm assuming that R is the base of an O-minimal structure. But and R, it looks like my real closed field, but I'm actually not assuming, I'm assuming that it's just a dense linear order. This theorem holds for an O-minimal structure over a dense linear order. A zero cell in R is a point. And a one cell is an open interval, possibly unbounded. So those are the cells in R. And now we define them iteratively. So if you have an I1 up to IN cell in R to the N, then an I1 up to IN0 cell in R to the N plus 1 is the graph of a continuous function. Definable continuous function. And an I1 up to IN1 cell in Rn plus 1 is the region between two definable continuous functions, f and g, with f less than g on the on the I1 up to IN cell. And a cell is one of those. Yes, from Rn plus 1, from Rn to R. Not defined everywhere. They only have to be defined on the cell. Right. So that defines a cell. Now we can define a decomposition of Rn is a partition into disjoint cells with a hereditary property that I haven't written out, but the projections with a hereditary property. That the projections, let's just say projections, also give you a partition into cells.
Rn to Rn minus 1?
Yes. Yes. Well, but also, right, it is also, and then also further projections. And it is compatible with a set A if each cell is contained in or disjoint from A. And then we've got the cell decomposition theorem that let A1, AK be definable in an ominomal structure. There is a decomposition compatible with each AI. Right. So I want to make a few remarks about this theorem, and I think then we'll maybe take a break. So one is, so this was proved by Knight, Pila, and Steinhorn, and you can also find the proof exposited very beautifully in Vandendrie's book. It's a completely elementary theorem. There's no completeness, compactness. You simply have this structure and your finiteness assumption. So you can see, for example, okay, in one dimension, it's the definition. If you have a set, it implies, of course, that every definable set is a disjoint union of cells. If you're in R2, then of course you can project and you'll find some definable set, which is going to be some points and open intervals, right? And then you can look over each one. Over here you'll have a copy of the reals and you'll have some other definable set. Over here you'll have some set, and then you'll pick out the lowest element, and that'll be some definer function, and then it'll be continuous at most finitely many points. It's a totally elementary argument. There's just a couple of key things that you have to observe are definable and which will give you the finiteness. The second thing is that this works in an arbitrary ominomal structure, and in this structure the only sets we know about are A1 up to AK. So the cell decomposition is actually, you can do this all in the structure of R just with those A's. In other words, you define things, what's the least element here such that you're in you can only use those sets. Those are all you know about. And this continuity statement is also a totally elementary statement. It's a really beautiful argument. Now, over here, I had definable where are my definable families? I think they've, I think they're gone, yeah. But when I wrote down my definable families, you may remember I put the parameters on the left. And that's so that when you cell decompose, you somehow decompose the parameters first and then all the sets. So when you decompose, and with this hereditary property, if you cell decompose a definable family, then in the process you have cell decomposed everyone in the family, every fiber. And finally, in the course of proving this, you prove something called uniform finiteness. So this is actually part of the proof. It's really a key part of the proof. But if you imagine that Y A is a definable set and YA is a definable family, let me just write it that way. Right, so these YAs are in some A to the N, and these parameters are in some, R to the N, R to the M. And suppose Z is a definable set. Let's say these are in R to the N. And Z in R to the N is definable. And suppose you happen to know that each fiber intersects Z is a finite set. Suppose you just happen to know that. Well, then the conclusion is that the sizes of those sets are uniformly bounded. And the reason is that the YA intersect Z are a definable family of sets, and they have a cell decomposition. And when you do that decomposition, when you get to the Rn variables, you're just going to see finitely many continuous functions on finitely many cells. And so you get a uniform bound on the size of families. And that's actually the key to the why O minimality implies strong O minimality. So I think this is a good time to take 5 or 10 minutes. So we break there. Yeah, so let's restart. So I put all of this down maybe a bit sketchily, but just to say that the I1 up to IN0 cell in Rn plus 1 is the graph of a definable continuous function on an I1 up to IN cell in Rn. So it's right. So you've got a cell, and then you have a graph over it. And similarly, the I1 up to IN1 cell is the region between two definable continuous functions, f and g, which are defined on an I1 up to IN cell. So then you have this picture. It's the region strictly in between. And the I1 up to INs are all zeros and ones. Yeah, so 1 is where you acquire more dimension. And so the dimension of the cell is simply the number of ones in that list.
And continuous is the order topology?
And continuous is in the order topology, absolutely. Yes. So that's really the key theorem. And it immediately proves that O minimality is preserved under elementary extensions and this key uniform finiteness property.
And if R is really a real number, can you say something like analytic?
So okay, good. I was just about to say what you can and can't say. So over a field, a definable function is differentiable, except at finitely many points. And so you can always upgrade the cell decomposition boundaries to be CK for any K. In general, you cannot do C infinity. That's a nice example of legal. So you can't. But sometimes you can do C infinity or even analytic. So in Rn-exp, you have analytic cell decomposition. But that somehow has to be, well, that has to be proven, but in general you can't have it. Now there's also, maybe I should, so that's the cell decomposition, maybe we should leave that. Maybe I can take this out. We can take out model theory and just talk briefly about the model theory free definition. Free that you can make of an O-minimal structure.
That's the model theory dash free definition, not the model dash theory.
The model theory free definition, yeah, which you sometimes see, and it's quicker. So it's very tempting, because what you note is that the definable sets in a structure are a collection of sets with a particular form. They're a collection of sets in AN for each n. And in each AN, the sets are a Boolean algebra. You can do finite unions and intersections and complements, and they're closed under projection because of the existential quantifier. And they have this property that the definable subsets in A1 are finite unions of points and intervals. So you often see this definition a sequence, let's say curly S equals S to the n. Sn is a subset of the power set of A to the n, let's say on a set A, ordered. Well, actually, does it have to be ordered? Well, you usually, actually, people in that definition, you usually do take it to be a field. So Sn is a collection of sets in A to the n, and it's a Boolean algebra. And you're closed under projections. And Sn contains every semi-algebraic set. And S1 is just the set of, is the collection of finite unions of points and intervals. This is the key. That's the key minimality property. So you can just say that, which you see often because it's easier than, well, it's just a straight definition. It's not very intuitive to work with that definition, for example, to see that the derivative of a definable function is definable. Okay, it's the complement of some, well, you can do it. But if you like, the model theory revenge on this definition is that this structure, this is just the structure, if you like, of A with all those S's. If you now say, okay, I'm going to make a model-theoretic structure and just stick in all those sets as my primitives, then it will give you the same definable sets. Okay, so I want to talk about parameterization. Next,
I'd also guess it's a bit cumbersome to directly describe like Rx in these terms.
You mean to describe all the definable sets? Well, in fact, the model completeness, Wilke's theorem gives you a very nice description of those. You just take two sets of they're all the projections of, so you actually do have a quite decent description. Parameterization. So this is a kind of, you can think of it as a kind of a dual to cell decomposition, but it says that a definable set Z in 0, 1 to the n can be parameterized in a nice way. So I'm going to define nice. Definition. Let Z be in 0, 1 to the n. Now, I should have said that once we have the cell decomposition, we have a good notion of dimension. The dimension of a cell is simply the number of ones that come up, because that's the number of times you took the region between two functions. When you take the graph of a continuous function, it doesn't change the dimension. And when you take a cell decomposition of any set, there'll be finitely many cells. Some of them may be points, whatever, but there'll be a biggest one, and that is the dimension. And it's very well behaved in terms of boundaries have smaller dimension, and I mean, it's a very well behaved dimension. So I'm going to suppose that my set Z has dimension k, and R is some non-negative integer, and R parameterization of Z is a finite set, capital Phi, of maps little phi from the open cube 0, 1 to the k to 0, 1 to the n. And I'm going to write phi, I'm going to write out the coordinate functions, phi 1 up to phi n. Each phi I is a CR function. Z is the union of the images. And so the key condition, I can squeeze it in, all partial derivatives up to and including order R are bounded by 1. In absolute value. So you can write your set Z as a finite union of images of maps from the right dimension cube, and up to this parameter that you assigned R, all the partial derivatives are bounded by 1. And so now I want to do this in families. This is somehow crucial in families. So this is just the family version. Let Z, which is in Y cross 0, 1 to the n, be a definable family. And for a family, we'll take the dimension to be the maximum dimension of the fiber. So I mean that each z sub y has dimension at most k. And then we'll say that a definable R parameterization of Z is a finite set phi of definable families little phi which map y cross 0, 1 to the k to 0, 1 to the n, and such that for all y in capital Y, the fibers, if you like, big phi y, or all these maps, little phi y, restricted to that point y, are an R parameterization of the fiber Z at Y. And the key point here, of course, is not only, of course, here the point is the finiteness and the bounded derivatives, but here the fact is that the same finite, you can parameterize all the sets in the family by the same finite number of these maps, and indeed they're all fibers in a family.
So there is no regularity when little y varies?
There's no what?
You don't ask for any regularity when the parameter varies. It's not
well, we don't ask for any regularity in y. Just for each y, right? All the smoothness, all the properties are just on the derivatives of that part of the function.
So you just needed to do it in a cell?
Well, these continuous functions, we're gonna, well, you do start with cells, but you have to deal with, yeah, I'm not sure I understand the question. There's no regularity on the parameters. Okay, so that's a definition, and of course the key theorem is simply that these things do exist. Let Z be a definable family of sets in 0, 1 to the n, and R a non-negative, well, a natural number, then there exists a definable R parameterization of Z. Okay, so that will be a really key, that's really the key, the heart of the counting theorem. So I'm going to say just a little bit about it. So for semi-algebraic sets, this is due to Yomdin and Gromov. So Yomdin did it in a slightly coarser way. He was happy to leave out little pieces of these sets. And the way it's framed here, where you absolutely parameterize the entire set, is due to Gromov when he presented this in a Bourbaki. And it does make things, if you know, at the end of somehow when you do this, things get complicated, of course, when the sets have singularities of various kinds. And if you're happy to leave out little bits, then it does make your life easier. And it can also make your life easier in point counting. So there are some nice, that idea has come back, if you like, that because if you want to effectively control this whole process, it can be much easier if you're prepared to leave out little problem areas, if you want to control how many of these functions you need for a given set. So I'm not going to prove this theorem. I want to prove one lemma that goes into it. The description by Gromov, the Bourbaki, it's in an appendix. It's quite an amazing few pages to read that proof. And there's sort of a more careful proof along the same lines by Binyamini Novikov. And essentially what you want to do is somehow, well, you start with a cell decomposition of some large smoothness, and then you want to just go through one derivative at a time and fix any derivative that's a problem. But when you fix one derivative, you have to make sure that you don't do too much damage to the previous derivatives. And also, well, I'm going to explain a bit what the main device is for doing this in one dimension. So maybe I should do this, and to make it effective is quite challenging. So let me put this on the board. I think it illustrates, well, one of the key points. Now, however, in doing this, so when you parameterize sets, one of the things you have to do is to reparameterize the functions that parameterize your set. So you might have a set which is the image of some box, and what you have to do in this process is somehow choose a deeper variable for that function to kind of smooth out some derivative. So I don't want to give the definition, and I just want to prove this lemma. So this is a really key idea. So let R be bigger than or equal to 2. And F from 0, 1 to 0, 1 is definable. And CR with the jth derivative in absolute value less than or equal to 1 up to R minus 1. And we suppose further that the absolute value of FR is weakly decreasing. So this is, if you like, it's part of the one-dimensional part of this problem. So you've got a function on 0, 1. And you can imagine that you've already sorted out all the derivatives up to the rth one. And when you get to the rth one, it's differentiable, but it's somehow weakly decreasing. So you've got a potential problem at the point 0, where this is unbounded. And of course, you can always, by O minimality, if you're given any function, you can subdivide it into the regions where things are weakly decreasing or increasing, right? And deal with the problem the other way, right? So you can always somehow, by finite subdivisions, reduce to this kind of case. And now you do this magic substitution you define g from 0, 1 to 0, 1 by sending g of x is f of x squared. Then g of j is, well, it's not bounded by 1 anymore, but it's bounded by some constants that are independent, that are only depend on, well, that don't depend on, that only depend on r, since all these are less than 1. So I'm going to call that strongly bounded. So you fixed the last derivative at the cost of maybe replacing this 1 by some number that depends only on r. That's what the strongly bounded means. And that means that this lemma will work in families. Because if you have some family of definable sets like this, then all of the subdivisions you need to make things weakly decreasing will all be uniform in the family. You can do it right by the cell decomposition and the uniform finiteness. There'll be at most 100 points you need to divide to make all those first 10 derivatives all weakly decreasing and whatever on intervals or increasing. And so although these are, you may have lost the bound of 1, if the bound is now 10 or something, then you can just divide 0, 1 into 10 pieces and scale, right? And then you'll make, I mean, right? You simply, you don't divide, you replace this by 10 intervals that cover this one, and you'll divide the derivatives all by 10, and then you'll recover. So once you have a fixed sort of a uniform bound on derivatives, you can then just fix that by scaling. And that's what you have to do generally, is you have to sort of fix this last problem derivative and only doing some kind of limited damage to the rest that you can then fix. And the proof is completely is trivial. You simply use the chain rule on this function g of x squared to write it as a sum j equals 0 to I of rho of ij of x fj of x squared. Rho ij is some polynomial, right? Absolute fixed polynomial, I mean, with integer coefficients. And all the terms are already bounded by some number, which depends on those coefficients, which are universal, except the I equals j equals r term. So all terms, what I call strongly bounded, except the last term, which is 2 to the r, x to the r, rth derivative, 2x to the r. And now the claim is that f to the r of x is at most 4 over x. And that's simply, it follows by the mean value theorem and the fact that we're weakly decreasing. So else, by the mean value theorem, you have some xi in x over 2 to x with f of r minus 1 of x minus f of r minus 1 at x over 2 equals f of r of xi times x over 2. But then f of r hang on, I've lost the thread of my mean value theorem. We have that. Right, but these are bounded by 1, right? So this is at most 2. On this side you have at most 2. So that's it. So that means that tells you how to do functions of one variable, although you have to notice the r, this only works when r is at least 2. So for the first derivative, you have to use the fact that you can look at the function either this way or this way, and you'll get a derivative less than 1. When r is 2 or more, you can use this trick to fix each derivative at a time. Now you can do this in families, if you have a family of one dimension of maps from 0, 1 to 0, 1. But now when you want to move up in dimension, you use a trick. There's a sort of a second trick, which I won't go into, that you view one of the variables. Let's say you're doing this. Well, you treat one of these variables as a parameter, and you, by induction, you assume you've done this. And then you've got the derivatives of this, and then there's a second trick whereby you reparameterize the maximum function of that rth derivative, and then there's a problem if that rth derivative is undefined at some point. And anyhow, there are some extra complications, but it's again, it's a totally elementary thing, and at the heart of it is that main one substitution. X squared will kill the next derivative. All right, so making this effective is quite difficult in general. In fact, it's not really possible in general, but in particular O-minimal structures, you can make this process effective. All right, so we've got this, there is a definable R parameterization. So finally, I can talk about point counting. So I should say that in my counting theorem with Alex Wilkie, the key thing was to prove that parameterization in the O-minimal setting. And the other part of it we'll see in a minute. So this now is point counting. All right, so I want to describe the basic case of a compact analytic curve. So I'm going to consider f from 0, 1 to the real numbers. So let's say analytic on an open neighborhood. All right, so this will be an Rn restricted analytic compact thing. This will be essentially my counting result with Bombieri. So I'm going to take the height of a rational number, P over Q, just to be the naive height. So here P, so R rational number equals P over Q in lowest terms. And I'm going to take the height of an n-tuple. This is for later. The height of an n-tuple will just be the max of the heights of the coordinates. For a set Z in Rn, I take the rational points up to height h. So here Z will be the graph. But for a general set in Rn, I can just take the points on Z in Q to the n whose height is less than h, and I can count those points. N of Z and h is the number of points on the set Z, rational points, up to height h. And then the theorem will be, in this case, so I'm sorry, I've got things a bit out of order because this somehow part, this is completely general, but then I want to go back and take Z to be the graph of this function. And the theorem is that for epsilon positive, n, Z, h is at most a constant, h to the epsilon, for any epsilon. Now here we're not going to reparameterize the set because it's already parameterized by this function f, which, okay, it doesn't have its derivatives bounded by 1, but they're bounded by whatever. Okay, so there's no parameterization in this step. But instead, we're going to use a lemma of H.A. Schwarz.
So F can be the identity.
Is it a transformant part of?
Ah, yes. I left off a key hypothesis, which is that this should be a transcendental function. Transcendental real analytic. I'm sorry, it means, yeah, no, there's no algebraic relation A of x and f of x that holds identically. Sorry, were there some other questions or the same? Yeah. Right. Well, it would be true if I simply counted on the algebraic part. I mean, on the transcendental part. But yeah, so here I simply want the function to be transcendental. All right, so here is this lemma. Which is due to H.A. Schwarz. Let d be a positive integer. J in R, compact interval. Don't think that's really. Phi 1 up to phi sub d, d minus 1 times continuously differentiable functions, and x1 up to xd points, and I'll take delta to be the determinant of phi I at xj. Then, for suitable intermediate points, Cij, intermediate to these x1 up to xt, and you can be a bit more precise. Delta, that determinant, is equal to the Vandermonde on x Vandermonde determinant times the determinant of the phi j minus 1th derivatives at the Cij divided by j minus 1 factorial. So that's a kind of mean value theorem. And the corollary is that this determinant is bounded by the size of the interval, by this Vandermonde, right? The length of the interval to the power d minus 1 over 2. That's how many pair products you have there. And just times some constant. So all of this stuff, those are just constants. The maximum derivatives, right? This is a d by d determinant, so it's d factorial times the product, whatever, of some bound on all those derivatives. So I'll simply call that C1, depending on those functions. But I mean, there's no clever estimate going on there. You just expand that determinant and bound everybody. Okay? The whole point is that this determinant is very small if these points are close together. Right. So now I can prove this theorem. So I'm going to fix a small d, at least 1, and let d be d plus 1, d plus 2 over 2, the number of monomials in x and y of degree up to d. And I'm going to suppose that xi and f of xi belong, they're rational points of height less than or equal to h, with xi belonging to my interval, some interval, which is a subinterval of 0, 1. I goes from 1 up to capital D, so I've got capital D points. And I'm going to apply the corollary to maps phi ij, which is simply the monomial maps in x and f of x up to degree d, small d. So those are my d functions, and those are my d points. And the conclusion from this corollary is that this determinant is bounded by some constant which just depends on f and capital D, because you're going to take up to, you have all these functions and they all have derivatives up to order capital D, and they all have bounds on those derivatives, times the length of the interval to the d minus 1 over 2. And now we're going to show that because all the entries here, so this is delta is this matrix phi ij, but it's all the xi f x to the j's at these points where they're all rational numbers of a bounded height. So we're going to show now that if this interval is quite small, then this determinant has to vanish because it's, well, you'll see, because it's too small to be a non-zero rational number of the denominator you can prove it has, but not too small. So the denominator of each row of delta can be cleared because x has a certain denominator which occurs at most up to power little d, and the same with f of x. So you can clear it by some ni, which is at most h to the 2d. Right? H to the d for x and h to the d for f of x. And you'll clear that denominator. And so if the determinant is not 0, so this is some integer, then it's at least h to the minus 2 little d big D. And the crucial point is that little d big D grows like d little d cubed, whereas big D minus 1 grows like little d to the 4th power. And right, so the crucial thing is the power of those ratios, and this, if you like, this is, well, this is the principle that's sometimes called the fundamental theorem of transcendental number theory, that there are no integers between 0 and 1. So let's call that by that fundamental theorem. If j, if you work it out, is at most some constant, depending on f and d, times h to the power 4dd over d minus 1, just the ratio of those, this and this, then delta equals 0. And if you clear that up, it says that if the interval j is smaller than some other constant, times h, if you just clear, you write down, d is d plus 1. This works out to be minus 8 over d plus 3. Then all points of z, q, h for x with x in j lie on one algebraic curve. And that's because if you take all of those points and make the rectangular matrix that it has rank less than capital D by this argument, and on the other hand, you can cover 0, 1 by some other constant, got by inverting that or dividing by 1, d h to the 8 over d plus 3, such intervals. So now you choose d such that 8 over d plus 3 is less than epsilon. And now you've proved that on your graph z, all the points up to height h lie on, so all points, all z, q, h points lie on this constant times h to the epsilon real algebraic curves of degree d. Now the intersection of z with any one of those curves is a finite set because it's a transcendental function. If you like, by O minimality, if it were an infinite set, it would contain an interval, and then it would hold, f would be identically algebraic. But by the uniform finiteness, there's a uniform bound on the size of all of those intersections. So that if you call these curves v, then z intersect v are of uniformly bounded size. And so that proves the theorem. Right. So what did I want to say here? Right. So I won't start with the multidimensional version, but one thing to notice is that in this proof, we didn't really need f to be analytic. We sort of only really needed what we get from the parameterization, that for, that you're given epsilon and you choose d, and now you just want it to be d minus 1 times differentiable on some number of pieces. And again, for this step, we didn't need, for this finite intersection step, we didn't need analyticity. We just definability would be enough. So Right. So, okay, so maybe I don't really want to start on the higher dimensional version, but maybe I might as well just state it. And then we'll take that up next time. So the counting theorem, which Alex Wilkie and I proved, it comes in a number of forms. So let me just maybe make this definition first. Take a set Z in R to the n. So actually this theorem does work in an arbitrary or minimal expansion of a field, but I'm going to switch to the real numbers just for. So I'm going to define the algebraic part Z alg to be the union over A, the subset of Z, which is connected, positive dimensional, and semi-algebraic, which we've seen means definable in the real field structure. And then the theorem says, it's essentially like this, that if you let Z be definable and epsilon positive, then there exists a constant such that if you exclude the algebraic part from your count, so the algebraic part of Z could contain algebraic varieties, lines, whatever, elliptic curves, anything, and they could have whatever kind of rational points they're permitted to have in diophantine geometry. But if you throw away everything, every positive dimensional connected semi-algebraic set, and count up to height h, then you get h to the epsilon points. So let me just stop there. There'll be a few different versions of that theorem that we'll return to next week. And the key point will be the parametrization, which this. Okay, so I'll stop there. Thank you.